Hi and welcome to the channel. It's Paseka Ditabe here and I'm back with another video tutorial for you guys. Today I'm going to be showing you guys how to build an ATS, which is short for automatic transfer switching. An ATS basically is a system that is typically used in applications where you need to have some sort of power backup. This is mainly used in hospitals and in industrial sectors where if you have load shedding, you can switch from one source to another. For instance, during load shedding, you could be switching on to a generator, and then when the power comes back on, the switch will switch again back to the municipal or ESCOM power, right? So I want to show you guys how to do this for yourself at your home, so that if load shedding happens, you guys can still catch your match or work on your PC, or maybe turn on the lights depending on the system size that you have. So without wasting any time, I'm gonna get into the video. And remember, there are a lot of links on the description. Check that out. And by the way, please do go and like, comment, share, and yeah, let's get into it. Thanks for watching. So the first thing that we're gonna do is that we're gonna go to the Eaton website, because they give some information on how to build transfer switches. And when you go to the website, and I will include this link in the description, uh, they will tell you what an transfer switch is, and then they go further to explain the different types of ATS systems. For instance, here they have an ATS where you can have two sources, utility, and another one such as a generator. And this is what we are going to be using. In our case, this would be the power that's coming from ESCOM here in South Africa, or your municipalities, right? And this would be your generator or battery bank that is connected to an inverter. And so what happens essentially is that when this power goes off, for instance, in the case of load shedding, uh, this generator is going to automatically kick in and power your system. And when the power comes back, automatically it will switch from the generator to the municipal power again. So that's what a ATS basically is. And when you go to the website, you can see there are cases where you can have uh, two utilities, or you can have two generators, sometimes more than one ATS in very complex systems. But for our project, we're going to be focusing on this type where I have the utility, and where my other source is going to be a battery bank that is connected to a inverter, basically, as you will come to see in the tutorial. So there you have it. Let's get started with the build. So remember guys, be safe when you're working with AC mains, because it can be dangerous and fatal. So getting started, um, first thing we're gonna need a den rail, and then we have our 24-volt power supply. It's an industrial one, 10 amps. and then we have our circuit breaker. And then on number 3 we have a relay, a finder relay. As you can see, it's 16 amps, 250 volts with a 24 volts coil. And then we have our terminal connectors. These are very useful in industrial connections. They're easy to mount, and they insulate your conductors, and also they make it quite neat. Um, so some of our other parts we're going to be using is a battery charger. Um, it's for an acid battery. We have a inverter which is 800 watts, and we're gonna use this module. The exact model number is a XHM603. Yes, so this is basically a charge controller, right? And we're also gonna need a bunch of conductors. So to get started on the build, okay, this is our DC battery, 100 ampere hours. So how we're gonna get started with this? We're gonna start with the conductor. As you can see, it has a neutral, a live, and a earth wire, and they have been stripped. So at the top of the first section of our terminal connectors, we're gonna screw in these 3 wires, right? Gonna tighten them there, and basically this is our AC mains that we are connecting to our system. This is gonna go to the mains 230 volts. Now that that is tight, we're gonna go to the um, bottom part of the terminal connectors. And so first, what we're going to do is we're gonna take another conductor, and we're gonna connect the earth, live, and neutral of these conductors to our power supply, basically. Um, so what's gonna happen is that our power from the mains is actually gonna uh, power this 24 volt DC power supply, which in turn is gonna close our relay contacts. So we take these ones directly to uh, the 230 volts connection that we just made. So as I said, when you switch on the power or you connect this to the AC mains, what's going to happen is that the 230 volts rather is going to power this circuit, which is going to close the relay contact and also feed power to the battery charger. So from the 24 volts, as you can see on the top, it has the 24 volt DC out, and I'm using these conductors to connect to this. So now that we've connected the conductors to our 24 volt supply, we're gonna go ahead and connect these 2 wires to the A1 and A2 of the relay. So basically, the A1 and A2 are is basically the coil. As you can see on the relay there, it says 24 volt DC. So by connecting this 24 volts to A1 and A2, we will be powering this circuit. And next we have the charger. It's a battery charger, 12 volt battery charger, with a maximum charging current of 6 amperes. And so what we're gonna do is that we take the conductors, which is the neutral and the live, and we're gonna connect it directly to the same terminals that power, uh, rather that come from the 230 volt AC. So again, as I said, when we switch on the 230 volts, it's gonna power the AC to DC converter, and at the same time power the battery charger. So when the power is on, say the ESCOM power or the utility power is on, uh, we're gonna be closing our relay contacts, at the same time charging our 12 volt 100 ampere hour battery. Those are the two main circuits of the AC. Basically, it's the DC converter and the battery charger. So what you see now is that we're gonna take another wire, this conductor, and also it's connected to the AC mains. Like I said, the first three ones I've spaced, like because I want to know which section is gonna be for the AC mains and so forth. So we take this live wire, which is from the AC mains, and it's going to the relays, normally uh, closed. Uh, no, it's going to the normally open rather of our relay. So what this means is that if it's in the normally open, if something is normal, it's in the normally open, it means that when the system is entirely off, uh, that the normally open contact does not make any contact. It's normally open. And then what happens is that when we actually switch the power on, because it was open, when we switch the power on, it actually closes. And then the one that is normally closed, it now becomes open. So that's how it really basically works. And so now what I've done is that I've taken two more conductors. As you can see, the one is actually like a kettle cord, and the other one is like a 3-pin plug. So the kettle cord basically uh, is because the inverter has that sort of an output, right? So what I wanted was that I should also have access to that output with a 3-pin plug, because if I want to charge things like cell phones or connect some other smaller load, I would be able to do that, right? Um, so basically, like I said, this one's gonna be for the lights. So at the same time, I'll be able to access that power with that sort of extension cord with a 3-pin header. So as you can see, this is the second section. This section is dedicated to the emergency source, meaning the inverter and the battery, right? As you can see, it has its own conductors, right? So that's the first thing you should note, is that you have the connections for the AC mains from the utility, and the next three are for the inverter, which is our emergency or backup power source. And what I'm gonna do next is on this connection. So basically, from the bottom, we're getting power from the inverter, right? But before this power goes to our circuit, our load, we need to run it through a circuit breaker, right? For protection. So I'm connecting my live on the top there and the neutral, and then I'm gonna find an earth connection anyway in the circuit and connect it with this one here, so that I know my system is earthed. And so the reason why we actually run this through a circuit breaker before taking it to the load is for the reason that if something is wrong with the circuit, or rather our load, if there is a short on our load, what's going to happen is that the mains is going to detect that fault and it's going to trip, right? And when the mains trips, automatically our backup is going to switch back on. So if we don't include this circuit breaker, what's going to happen is that we're going to have an emergency power source that comes on to a faulty circuit, and that is going to be tragic, especially if it's a short circuit. This thing is just going to heat up and it can cause a fire. So what I'm doing is, by running it through a circuit breaker, is that if there's a fault in the load that has been detected by the mains, it will also be detected by this secondary source, which is the inverter. So it will also trip. So if there's a fault in our load, both systems will be off, right? So if you don't put the circuit breaker in, it's going to be tragic if something goes wrong. So make sure that you have a circuit breaker there that works perfectly. So as you can see, uh, I'm installing these wires to run through this breaker. If the contacts are a bit loose, try and make them thicker by using these terminals at the end. So they kind of increase the circumference of your wire. That way they can grip, because these things are actually meant for higher loads. Make sure that your connections are not loose. Try pulling them out. And there we have our earth that we're going to connect to any other earth on the system. And I've chosen the terminal that's closest, and that is the one on the power supply. That's our closest earth connection. And yeah, that is fine. And now we're doing the neutral. I'm also gonna look at the closest one that I can find. So now that I've run my live through the circuit breaker, I can now take it to the relay where it can be switched. So this one basically is gonna go to the normally closed. So what this means is that when there is no power, this circuit will come on. uh, Normally closed, it means like in the absence of power, if it's not on, it will be closed, right? And so it will close in between the load and the inverter. Also check the sketches that I've provided, and at the end of the video I also do a walkthrough of this video in the schematic format so that you get a real understanding. So our load in this case is a smaller wattage bulb, right? It's an incandescent bulb. This is something that I use always when I'm working with these circuits or any other circuit where I need to test the load. Start with a smaller load. That way, you know, if something is wrong, you might damage this smaller load. It's nothing expensive, you know. So the load is connected to the common, which is rather uncommon because in many events, the common is a power supply. It's actually the power, and then you connect your load or loads to your normally open and normally closed. But in this case, our common becomes a load, right? So our load is common between the two supplies. And what I'm gonna do next is uh, take this the neutral and connect it to the AC, So let us check. So now that we have our load connected, what I'm gonna go do next is take the inverter and connect it to the circuit. So the inverter is gonna be connected to our battery. So that's the wire that goes to the inverter. It goes to the output of the inverter. So it's sort of like a kettle cord connection that they use. So there we have it. So this is the output. There's the AC output, as you can see, and the red and black wire, those are the DC 12 volt inputs. So basically, those are the connections where that actually go to the 12 volt battery. So what the inverter does, it takes the 12 volt DC and it converts it into 230 volts AC sine wave. So this is our battery. And again, remember that you need to include a fuse into your circuit, because as you can see there on the left, that's what happened when there was some fault when I was still testing the circuit earlier. And luckily these terminals are made of lead, so during high heat these things turn to they melt and they actually fall off, right? Which is, I think, also is a safety feature when you think about it. So this one broke off because of too much current that was on the circuit, and I didn't have a fuse. So now the battery terminal is damaged. So first I start off with the power, the positive, and then go to my ground. So realize that the red wire, you have two red wires. The one is from the inverter, and the other one, actually, with the clamps, the red and black, those are from the um, battery charger, right? Because the battery charger also takes 220 volts and outputs 6 amp uh, DC, right? So that's why you have two connections there. And you will see later on we're gonna be cutting those wires and running them through a charge controller before they actually get to the battery. So now that we've assembled this, we're gonna go ahead and plug and see what happens. And as you can see, the light goes on, the power supply goes on, and as you can see, the light on the charger also goes on. So next, what I'm gonna do is actually pull out the plug to simulate sort of like a load shedding situation. As you can see, all those lights go off, and next our power goes on. There's a bit of a delay there, but as you can see, the lights to the charger and the 24 volt supply are off, and now they're back on. So in this section, I'm gonna connect the charge controller, because if I don't use the charge controller, my charger is just gonna continue charging the battery, and that's gonna damage the battery due to overcharging. So what I'm using here is this XHM603 DC battery charger. As you can see, you have the in and then you have the battery. So what you see now are the terminals of the battery charger. So the first thing that we're gonna do is we are gonna connect the battery terminals, right? As you can see there, it says bat. So we're using these connections to connect to our battery. And once we've done this and clamped them down, we're gonna have our set points for the battery. So these terminals go directly to the terminals of our battery, right? And we're gonna clamp them down. Now once you clamp them down to the battery, you're gonna see this default 12.7, right? So this happens regardless of what battery you put in. So using the buttons there below the screens, we're able to set our threshold to say this is when I want you to start charging at this voltage, and this is when, and then the other one is when you want it to stop. So how you do that, and again realize that the power there at in, there's nothing connected at this stage. We're still at the battery voltage, right? And so what we're gonna do now is actually set this. So you long press the button on the right to set your upper limit. So for instance, I'm scrolling down and saying I wanted to stop charging at 13.5. It will start blinking. And then once it stops, that is our set point for where it needs to stop charging at 13.5 volts when the battery gets to 13.5 volts. And I'm gonna do the same on the left button, right? And on this side, what I'm doing basically is setting the voltage where um, the battery needs to start charging, because when the battery says reaches below 12 volts, then you know it's flat. So now after long pressing, I'm gonna go through it and say let's go up until, let's see, 12. uh yes, 12 volts. So it's gonna blink and go back to that 12.7. And so when I press there, it goes 12. When I do the other one, it's gonna say 13.5. So it shows that our limits have been set, right? So now we know that it's gonna charge at when the battery goes to 12 volts, and it's gonna start charging when our battery voltage goes to 13 volts. And so now what's left to do is to connect the in, which is basically the output of the battery charger. Realize at this stage it's not yet on. I have not switched it on yet, and you should only switch it on once you've done the connections. And also be careful of the polarity, right? You have a positive and then you have a negative. In this section, I'm going to be showing you guys the schematics just so that you get a much clearer picture of the design. And I've used Design Spark Electrical for this, and this is free electrical CAD software that you can download, and I will include the link in the description so that if you want it, you can go download it for yourself and actually learn this. This was my first time in fact using this. It's not the best sketch, but it really does help in you know assisting you to get the bigger picture. There are a lot of things that I said that I find that maybe are not clear, so the sketch will help clear things up. So the first thing that you will see is that we have the yellow, I mean the blue, brown, and the green, which represents the 230 volt AC from our mains, right? Meaning this is the utility power. And the same as in the sketch, as you will see, starting from the left, right, is that you will see that in this section you have the 24 volts AC to DC supply with a 24-volt output that goes to the A1 and A2 coil of the relay. And then going further right, just closer to the 24-volt power supply, you have the live wire that is going directly to the normally open of the uh, relay, right? And so this wire basically is uh, the one that's gonna connect your mains power to the load, which is lighting load. And as you can see, they also have the normally closed, which connects the inverter source. So to move in sequence, if we go to the far right, you'll see there is a battery charger, right, that is connected directly to the battery. Notice that the battery charger is similar to the power supply because it takes AC, converts it to DC, but this one is 12 volts and is used to charge the 12-volt battery. In this section, I did not include the fuse and the battery charge controller, which would have been in series with the battery charger before it actually goes to the battery. So when you look at it, is that when the 230-volt AC mains is on, you will have the 24-volt power supply um, on, activating the relay, and another circuit that's going to be on will be the battery charger charging the battery, right? During the time where the utility power is still available. So essentially, we have two different circuits, which is the um, the mains or the utility circuit, and then we have the battery and inverter circuit that come on in different situations. If the utility is on, it will be the utility that supplies the power, and if it goes off for any reason, the inverter circuit will then kick in and take in the load temporarily until we have our mains voltage come back on. So if you follow the circuit, especially when you look at the relay, you will see that in the instance where the power is off, we have the normally closed, meaning if you look at the load, you have it connected to a neutral, and then through the common and all the way to the normally closed, going to the inverter. Now, if the power switch is on, meaning the utility goes on, what will happen is that that switch will now transition to the normally open, and that is the one that's connected to the AC mains. If you don't understand this, if it's still confusing, uh, I'll post some other links again related to relays, and you can go check that out and see what this all means. But this is a relatively simple circuit that you can build if you have these types of material. Remember again that for this circuit, we could have changed the load into something else depending on the system size. You don't have to use exclusively a battery or inverter. Could have been a generator, right? That is the emergency supply, or a solar powered system, you know. So this is just how I used it, but you can use it in so many different ways. And again, you can go to the Eaton website to actually check the different configurations that you can set for ATSs. So in this part of the video, I'm going to be focusing on the embodiment of the project because I wanted to be protected and I wanted to look neat when it's up on the wall, because I'm going to be doing this practically with a real DB box, right? But there's rust bucket, but it will do the work uh, of actually making the work neater and to protect it. So the first thing that I'm going to do basically is to see if the entire circuit can actually fit in here. uh, I don't think we're going to be using any trunking for this. I've made my wires solid and isolated, but trunking would have not fit in here, so I had to actually remove it. So now that I know that it actually fits in here, I'm just gonna do all my measurements for the drilling and then go ahead and actually start to work on the box. So now I've uh, cut out that 3-pin uh, plug, and what I'm gonna be using now is this household uh, wall mount socket, because it just looks neater and more practical. So now if I need that extra or access to this extra power, I can easily access it on the side of this panel. So the first electrical cable that you see from the top all the way to the bottom, that is the load. That is um, the wires that go to the lighting load, basically connects to the entire lights of the house, and the second wire from the bottom, as you can see, is coming from the DB box. That's the mains power, as you can see, right? So I know that this works here. Also, there's the inverter connected to the battery. And so, like, I always like to do this, take the project, not just as tutorials, but to use them in real life. Because I mean, that's the purpose of it in the first place, to say build something that actually works, something that you or other people can actually find useful. And so right now we're doing the same connections as we did in the tutorial, but in the practical applications. And as you can see, it's pretty much similar, just that again you're working on very high voltage, so you have to be absolutely careful when working with this. So you can see the entire system there. For demonstration, I'm gonna switch off this mains, and you will see as I flip the switch, everything goes off, the lights go off, and then as soon as the lights go on, and then you will start to hear the inverter going in. So you keep it up. If I switch it back off, the power supplies are back on. This is basically to simulate what would happen if you had, say, load shedding, right? You'd have the system then switching back and forth between the mains and the emergency power supply. And so to end it off, I just wanted to show you guys how it looks like, in a real application. I have a lot of lights here at the restaurant, so it looks quite cool when the whole town actually looks dark, and I have the whole place lit up. uh but then again, thanks for watching.